In this video, I'll present the mathematical models that are associated with electric charges, forces, and fields. So first, we have this one, F equals QE. F, this is the electric force. Q is the charge, electric charge of a particle that's feeling the force, and E is the electric field at the location of the particle. In this first equation, this tells you the force on a particle that's inside an external electric field. This electric field is also related to a charge, but it's different. This time, this is the electric field that's created by the charge Q. This relates vectors. The bottom two here, these both are magnitudes. So these are scalars. This is the size of the electric field. This is the size of the force. This gives you the magnitude and direction. So the electric field created by a charge Q is given by K. This is a proportionality constant that's sometimes called Coulomb's constant. This is why in a previous chapter I used not a K but a KB for Boltzmann's constant. This is a different constant. Okay? So this is the one that goes with Coulomb's law. So K times Q divided by R squared. This R is the distance between the charge Q and the point that you're interested in. Okay, so this is the magnitude of the field created by Q. I've put in here the value, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared for this constant. And then this R is the distance from the charge Q. Now the last mathematical model here, this gives you the magnitude of the force between two different objects, 1 and 2. So the magnitude of the force is K, again it's the same K here, Q1, so this is the charge of one of the objects, times Q2, the charge of the second object, divided by R squared, the distance between the two objects. And you can see that this force here, this is just, if you look at the, say, electric field, if we call this an E1 caused by a Q1, if we put a charge Q2 into that, then the force on it would just be Q2 times the E, and that's exactly what this is. So this is KQ over R squared times the second Q. And remember, this gives magnitude only. You still need to work out direction. Electric flux. This is given by the symbol phi. This is a capital Greek letter phi sub E. So electric flux is electric field, E, times the area. Remember, flux is the electric field passing through a surface. So the area of that surface times the cosine of the angle between the area and the electric field. So here I've added as an example an area. It's hard to draw three-dimensional objects on a two-dimensional space. But anyway, this is supposed to be a plane that's here. So we've got some area that's sticking out this way. The direction of that area is out from the surface. So this is the normal vector of A. So these are magnitudes. The magnitude of E times the size of this area. But then the theta is between the E vector, so you still have to know what direction the electric field is going, and the area vector, which is normal to the surface. This equation is only valid when the electric field is constant over that surface.